Welcome to today's video where I'm going to discuss an application of limits. I'm going to show you how you can use limits to calculate the slope of a tangent line drawn to any function. Now before we can do that, I'm going to review some concepts from linear relations that you would have come across in Pre-Calc 11, would have done a little bit in Foundations 11 as well. So a couple of quick formulas just to make sure we're familiar with. First one is how to find the slope of a line if you know two ordered pairs in the line. Change in y over change in x, so the y2 subtract 1 divided by x2 subtract x1. That will give me the slope of any line. So we're going to need to use that. This formula here, called the point slope form, is one you can use to find the equation of a line. And we will be finding equations of straight lines. And another one down here can also be used to find the equation of a line. However, this one's usually more beneficial if you are given the slope and the y-intercept, and it's called slope y-intercept form. But it could also be used to find the equation of a line. I will predominantly, though, use this one unless I was told the y-intercept in the question. Well, then I might go to this one. Okay, so let's look at just a couple of examples of how to use this stuff. Let's suppose I wanted to get the equation of this red line that I see on here. Well, there's a couple of points that have been highlighted for me. So as soon as I say find the equation of a line, I say, well, I need to use this formula. Y minus y1 equals m onto x subtract x1. That's called the point slope form. It's used to find the equation of any straight line. Well, I can't use that. Well, let me just... So it's called, again, the point slope formula. Well, it's pretty much self-explanatory. You need to know one point on the line. I've got two. And you need to know the slope of the line to use this formula. M represents slope. X1, Y1 represents the coordinates of any point on the line. So we have two to pick from, either this one or this one. But my dilemma is I need to figure out the slope. So I'll just do that first, which is easy enough. Calculate the slope. I'll go call this one y2, so 3 subtract a minus 1. And then the x's will be negative 3 subtract 3, giving me a slope of 4 over negative 6, which is, in simplest form, negative 2/3. That is the slope of this line. Okay, so I know the slope. I've got 2 points to pick from, and away we go. So I'll use this one. So y subtract, the y is a negative 1, so it'll be y plus 1. The slope is negative 2/3. X subtract, the x coordinate is 3. I'm going to go to what's called standard or sometimes general form. I don't want any fractions in it, so I'm going to multiply this whole equation by 3. So I'll multiply this one by 3, this one by 3, and this by 3. Now this is all considered one term because they're multiplied together, giving me now 3y plus 3. This 3 will get rid of that. Negative 2, but then it's going to get multiplied by the bracket, so negative 2x, and then negative 2 by negative 3 is a positive 6. And then in general form, we want our x to always be positive. So that means this term is going to have to move. 2x plus 3y, move this one over. And there I would have the equation of that straight line. If I rearrange that to the other, so this is called standard or general form. Again, sometimes interchanged with standard, depending on who the person is or the book you look at. And then there's also what's called slope y-intercept form, which is acceptable if you're not told to put it in one. Slope y-intercept form is y equals mx plus b. So if I rearrange this, it would be 3y equals negative 2x plus 3, divide by 3, divide by 3, divide by 3. So in y equals mx plus b form, it would be negative 2/3 x plus 1. I don't know if any of you noticed, you could actually see the y-intercept here was clearly 1. That's the b value. So I could have went right away and said, hey, I know the slope. Now I know the slope and I know the b. And I could have right away went to this form. So y equals negative 2/3 of x. Y-intercept is 1, so that'd be a plus 1. Same thing I got doing it that way. Continuing on, now this is not stuff that's new. This is grade 10 stuff you do in Nerf 10. I do find those students are a little rusty on it sometimes when we first get going on this, so please make sure you refresh your memory here on how to get the equations of straight lines, slopes of lines, what do I mean by y equals mx plus b. These are just prerequisite skills we would hope that students have acquired before they arrived in a pre-calc 12 course. Okay, I got another example here. This one brings into play the word perpendicular. So this would draw upon you hopefully remembering that lines that run parallel, like this, have equal slope. And hopefully you know that the word perpendicular means that two lines that meet at a right angle, they have what are called negative, or opposite, negative reciprocal slopes. All right, so let's see what my dilemma is here. I want to find the x-intercept of a line that passes through this ordered pair and it runs perpendicular to this line. Well, x-intercept is found by letting y equal 0, but I can only do that if I know the equation of the line. So I just want to, if I go back a slide, imagine if this had said determine the x-intercept of the line shown below, and I wanted to calculate that. I would have done this same work. And then when I got to, probably I'd use this version up here, right? And I would have just said to get the x-intercept, all I would do extra at the end is fill in y is 0. So this would have been 2x minus, or plus 0, minus 3 equals 0. 2x is 3. The x-intercept is 3 over 2. If I look at that, that is exactly what the x-intercept is. Right between 1 and 2, 1.5. So that's how I would calculate the x-intercept. So we are going to have to first, here's our plan. We're going to find the equation of the line. And then, once we get the equation, we will let y equals 0. And that will let us get the x-intercept. So that's our plan. Well, let's see if we can do that. So to find the equation of any line, this is the first thing your brain should think of. Point, slope, form. I need to find a point on the line. Check, I know that, that's easy. So there's x1 and there's y1. I need the slope of the line. That's not quite as easy. They didn't tell me the slope, but the key word was perpendicular, and us being solid math students, knowing that lines that are perpendicular have negative reciprocal slopes. Well, I'm going to take this line, 2x, take away 3y plus 6 equals 0, and I'm going to find the slope of this line. Now you may say, well, how the heck are you going to do that? What I'm going to do is rearrange it and make it look like this. And then the slope will be the number stuck right in front of the x. Now what students will do wrong is they say, oh, I know, oh yeah, the number in front of the x is always the slope. No, the number in front of the x is the slope if you isolate the y equals by itself. So I have to do a little rearranging here first. So 2x plus 6, I'm just going to take the negative 3y to the other side, divide everything by 3, and I now know that this line is the form y equals 2/3 x plus 2. There's the slope of this line. It has a slope of 2/3. Now, I don't want the slope of this line to be the same because the line I'm getting the equation of, this one over here, is perpendicular to this line. So a line that is perpendicular would have a slope of negative 3/2, negative reciprocal. Now I know the slope of the line I want the equation of, and I know a point on the line. We are in business. Let's fill this in. So y minus y1 equals my slope. Slope is down here, negative 3/2, onto x minus x1, which is a negative 5, so that'll become plus 5. So this line has the equation y minus, actually I'm going to get rid of those fractions again, so I'm going to go 2y, take away 4 is negative 3x minus 15. So I didn't show it, but this is what I did. I multiplied everything by 2 to get rid of that fraction. Now I'm going to, so I could rearrange it and put it in one of those formats, but I don't have to because it didn't ask me for the equation of the line. I wanted the x-intercept. So right now I'm going to let the y value be 0 and see what I get for x-intercept. So this is going to become 0. Take away 4 is negative 3x minus 15. Bring your negative 3x, or it doesn't matter. I guess I'll bring that over there, and I'll take that over there. And I will get x-intercept of negative 11 thirds. All right, so that's a problem. I made that one pretty much as challenging as I could. It threw everything at you. So I talked about intercepts, I talked about point, and I had to use point slope. I talked about how the connection with negative reciprocals, how to find the slope of a line if you know its equation. So there's a lot of stuff from NERF 10 that we had to rehash out here and be able to hopefully dust off in our brains and now be able to use. Okay, so nothing I've talked about here has anything to do with calculus or limits, which is what we're doing right now. So what we're going to do now is try and show you how you can use some of these concepts we just talked about and limits together to find the slope of a tangent line. So a tangent line to a graph is a line that just touches but doesn't intersect a graph at a particular point, and only at one point. So for example, this line is not a tangent. Someone said, oh, well, it only cuts it at one point. But the rule is it can't intersect. It has to just touch. So if I wanted a tangent line, let's say over here, that's a bad one. You get the idea. I'm trying to draw this kind of sideways, but imagine that touched just in one spot. That would be a tangent line. The red line you see here cuts it in two spots. That's referred to as a secant line. So I want the slope of this green line. Well, the theory behind what we're going to do is we're going to pick, so this is the point where this is called the point of tangency. And I want to get the slope of this green line. Well, the dilemma you would say, assuming I know what this function is, I could get the coordinates of this point, but that would be the only point I know on the tangent line. So the dilemma is I can't get the slope unless I know 2 points on a line. Well, what we're going to do is pick another point somewhere on the function, and we're going to draw a secant line. And we're going to use the secant line to approximate the slope of the tangent line. Now, when you say approximate, you say, okay, well, I guess it'll just be close. But we are going to approximate it so that it is so close that it is going to be the exact answer for the slope. And I'm going to show you how we're going to do that, and it's going to draw upon our knowledge of limits. If you can envision what you see here right now, if I found this, so that let's call this M, and let's call the slope of this line M2, let's say. If I was to get the slope of this secant, would you rate it as a good approximation for the slope of this green line? Well, I hope you'd say it's not great. It's not terrible, but it's not a great approximation. Certainly, it's going to be a significant difference in terms of the steepness of this line compared to this line. Well, the theory behind it is I've picked this point, which was the one where the tangent line was drawn, and then I went just slightly to the right of it, and I picked another point. So I went up and said, well, where do I hit the graph? And I drew my secant line. What if I had gone maybe not quite as far away? What if I had only gone over to here and drew my secant line now? Maybe I'll use this to make a better line. And drew my secant line through those two dots. Do you see how if I had moved that point a little bit closer here, right? Instead of this far away, so now I'm only this far away instead of this far away. Well, the line gets to be a little bit better. Well, the theory behind it is if you keep moving it closer and closer, you're going to get a better and better approximation. So if I look down here, so imagine that my first point I picked was way over here, and this was the secant. So the pink line right here is the tangent. So this was my first approximation. Well, and this was my point, so let's say this was my x value, and I went however far h, I went h units away over here to x plus h, and I picked another point, and I drew a secant. Well, I think you'd say that's a terrible approximation for the slope of that line, and I'd agree, because it's too far away. Say, okay, why don't you move q a little bit closer? So I say, okay, let's go to here now instead. So we'll just make h a little bit smaller, and we'll just go to there now. So now this is h, and we get the slope of this secant line, because I'd have 2 points. If I know 2 points on a line, I can get the slope. Well, that's still not great. Say, okay, well, why don't you move q even a bit closer? So now I'm over to here. Can you see how this blue line is moving around as I get closer, and it's starting to match up with the slope of this line? Well, the theory is, imagine that this point was even, well, I'm going to draw it so we can still see it. Here, like it is. Use that one again. Oops. What did I do? There. So now, if I get my line here, now see how the point was getting closer. I think I was at about here now. If I look at this, I was somewhere around here for my point of tangency. So again, now the distance between x and the other point was only this small little distance. Now, hopefully some of you are sitting there watching and saying, I think I see where he's going with this with calculus and limits. The theory behind it is, why don't we keep moving this point over here so that it's so close to this one that it's basically on top of this point. And then those points, when they're so close together and we draw the line that runs through the two of them, it's basically going to give us a secant line that lays right on top of that tangent line. The notation I'm trying to get you to think of is we want h can't equal 0, but we want it to approach 0. H being the distance between the two ordered pairs that we have, the point of tangency and the point that we choose. H can't be equal to 0 because if you don't move anywhere, you've got the same point, so you don't have two separate points. But if you have a point and then you ever so slightly move to the right of it and get another ordered pair, and you use those 2 points to find your slope, you're going to get an answer for your slope that is pretty much identical to the slope of that line. And the theory behind it is because we can make that point so close to this one that when you draw the line that connects those two and makes a secant, it'll pretty well have to lie right on top of the tangent line. So if I put that into a formula, let's go back to my diagram. So here's my diagram. X is the ordered pair. F of x is the y value when you fill x into your function, whatever this. So this is your function y equals f of x. I have no idea what it is, doesn't matter. This is just generally the rule that will work all the time. Then I'm going to go over h units away. I'm kind of blowing this up so we can see it. And I'm going to get another ordered pair, which will be x plus h. That'll be the x value. You'll fill that into the function to get your y value, which will be the function evaluated at x plus h. And you will have the slope of your secant. Now let's get the slope of this secant. Knowing this formula, the slope between any 2 points is y2 take away y1, x2 subtract x1. So here's my 2 ordered pairs. Let's write out the formula. So the slope will be y2, f at x plus h, subtract y1, which is f of x. All of that will get divided by x1, which is x plus h, minus x2, which is x. If I just clean up that denominator, f at x plus h minus f of x, all over x plus h minus x will just give me h. This will be the slope of that red line. Here's where calculus will now, but that's not what I want. I want the slope of the tangent, the pink line. and one simple little designation. So here's what I'm looking for, the slope of the tangent line. Well, I just said to you, what I want to happen is h, the distance between the two, that's what h represents right here. I would want that to become as small as possible. Calculus, limit, as h goes to 0, of f of x plus h, subtract f of x, all divided by h. You will come to find out eventually this is one of the most important formulas in all of calculus. Later on, we'll eventually refer to this as a derivative. So if you ever see something you're talking about derivatives, you say derivatives. This is, eventually you will find out the definition of a derivative. But for now, we're just going to call it the slope of a tangent. And that's how we're going to calculate slopes of tangents, using this formula. Okay, so let's put this to play and see if we can make this work. So I've got a situation here. I've got a curve, y equals x squared plus 2. So that would be my f of x. F of x is x squared plus 2. I want to draw a tangent, and I want the equation of this blue line. It says at the point when x is negative 2. All right, so when x is negative 2. Okay, what I'm going to do then is find my slope first. So the slope of the tangent, I suggest you write the formula out in the beginning until you become comfortable with it. It is the limit of f of x plus h, subtract f of x, all of that, divided by h, as h goes to 0. All right, what I often like to do is go over here to the side somewhere, just where I've got a little bit of room, and figure out f of x plus h. So I know that the original function f of x was x squared plus 2, I think. Yeah, x squared plus 2. Well, we finally get to put that function notation information we learned in pre-calc 11 to work. So this means put x plus h in where the x is. And I like to simplify these as much as I can before I go and put it in the formula. So f of x plus h will be x squared plus 2xh plus h squared plus 2. So there's f of x plus h. Let's go up to this formula. The limit as h goes to 0, f of x plus h. This expression is f of x plus h. X squared plus 2xh plus h squared plus 2. Subtract the original function f of x. That's this. X squared plus 2. All over h. These will always generate indeterminate limits, but they will be indeterminate limits that we should have the capability of eliminating that situation. Now, watch what happens here, and this is what should happen every single time. You should be able to get a common factor of h that you'll be able to get rid of down here. X squared, subtract x squared. That's gone. Plus 2, take away 2. Those are gone. The only thing left are these two terms, and notice they have a factor of h in them. So I'm going to factor that h out. That'll leave me with 2x plus h, all of that over h. Indeterminate situation fixed. What I now have, so h can go to 0. Now it's h going to 0, not x. H is going to 0, so there's still an h left here. So it's going to be 2x plus 0 will be your slope function. And what you now have is a slope function. You could have done this question by filling in the x is negative 2 up at the very top, which you'll sometimes see done in examples. I prefer to do it generically. I always just use x every single question, and then at the bottom I fill in my x value to get my slope at that particular value. The benefit of doing it this way is, let's suppose there was a part B that wanted me to do something with a tangent line drawn when x is 3. Well, I wouldn't have to do all this work again. I would just fill in x is 3 and I'd know the slope of that tangent line. This will give me the slope of a tangent at any x value. And in this particular question, we are going to use x is -2. So at x equals -2, our slope is 2 multiplied by -2. I have just figured out that the slope of this blue line is -4 using limits, which is going to help me now get the equation of the line. That's why I reviewed that for you on our slides prior to this. So to get the equation of any straight line, it's y minus y1 equals m multiplied by x subtract x1. Well, I know the x value and I know the slope, so the only thing I'm missing is the y value at this particular point. So if x is -2 and I want to get the y value, well, the y value is found by filling in x into your function. So just fill -2 into your function for the x, which will be -2 squared plus 2. That's going to give me 6. So this ordered pair is -2, 6. So now look what we know. We know a point on the tangent line, and we know the slope of the line. That is perfect. That's what we need to use this formula down here. So y minus y1 was 6. The slope was -4. X subtract a -2, so that'll go to +2. And you usually will put this either in standard form or y equals mx plus b. I don't really care which one you use, unless you're told to pick one. I personally like standard, where I make it always equal to 0 and x positive. So everything's going to go this way. 4x plus y plus 2 equals 0. So remember, in standard form or general form, x must be positive, and you're not allowed to have fractions, and you have to have it equal to 0. There you have the equation of the tangent drawn to that graph at x is -2. And we used calculus. I got 2 more that we're going to look at. So it says, for each of the following, find the equation of both the tangent line, and then here's a new term, something called a normal line. That's new. I don't suspect anyone has ever seen it. It's not very complicated, but it's a new term. This is a normal line. So you have a graph, let's say, and then, terrible tangent, and you draw a tangent line, like so. Okay, so this is a tangent line. That's what we just did. You ready? That is a normal line. A normal line is a line that runs through the point of tangency perpendicular to the tangent. So the important aspect there is we're going to do it as if it were a tangent. We're going to get the slope of the tangent, and then we're going to use our connection we know about right angle, lines that meet at right angles. We're going to take the negative reciprocal of our tangent slope. All right, so you don't do anything really any different other than at the end, take the negative reciprocal of the slope of the tangent, and that'll give you the slope of the normal. So let's take this one. Actually, that one's pretty similar to the one that I just did. How about we do this one? Because I'm not going to do both of these. Let's do this one. Y equals the square root of x minus 1. So this is my function. So f of x is the square root of x minus 1. F of x plus h will be the square root of x plus h minus 1. Now hopefully you know why I'm doing f of x and f of x plus h, because to get my slope, I'm going to need to use this formula. Oh. The limit, right, so the slope of any tangent line is the limit of f at x plus h, subtract f of x, all of that, divided by h as h is approaching 0. So I'm going to f of x plus h, so limit as h goes to 0, square root x plus h minus 1 minus square root x minus 1, all of that divided by h. All right, let's clean this up and see what we're dealing with here. So limit as h goes to 0, square root of x plus h. Now this minus 1 and this minus is going to go through here and switch that to a plus 1, so they're going to wipe each other out. So I'm down to this. So now we draw upon our knowledge of limits. This is indeterminate because if h went to 0, I'd have root x minus root x, which is 0, over h, which is 0. Well, we've seen this situation before. We're going to rationalize. Square root of x plus h plus the square root of x, square root of x plus h plus the square root of x. And I'm going to expand that out now. So limit as h goes to 0. So these are conjugates. Root x plus h by root x plus h is x plus h. Take away the square root of x times the square root of x is x. H will stay here. Square root of x plus h plus the square root of x. Simplify the numerator. H goes to 0 of x plus h minus x is just h over h. So again, anticipating what's supposed to happen and looking here saying perfect, that gets rid of that. And I now have, remember this formula is used to find slope. So now that I'm at the point where I can figure this out, so the slope is 1 over, now remember h is going to 0. So it's square root of x plus 0 plus, that should have a root x on it, plus the square root of x, which is the same thing as 1 over radical x plus radical x. 1 over 2, I just collect like radicals, 1 over 2 radical x. So this question wanted me to get the equation of both the tangent line and the normal line when x was 9, and the original function was square root x minus 1. So let's not lose track of this. So y equals square root x minus 1 at x equals 9. Well, let's get the point of tangency. So my point, because they only gave me the x value, so once I know the x value, to get the y value, you fill it in here. Square root of 9 minus 1. So y will be 3 minus 1, which will be 2. So I know the point of tangency is at 9, comma 2. So there's my point. Let's do slope of the tangent. So the slope of the tangent, and again, we're dealing with the situation where x is 9. So slope will be 1 over 2 square root 9. The square root of 9 is 3 times 2, so it's 1 over 6. Go to your formula, y minus y1 equals your slope, 1/6. X subtract your x coordinate. I'm going to go standard, so I'm going to multiply everything by 6. 6y, subtract 12. Get rid of this 6, you'll have just x minus 9 left here. X is positive, so we're going to move these two over. X subtract 6y plus 3. There's the equation of the tangent. And I'm going to do it again to do the normal. But I don't got to do all this work over again. The only thing I got to change is this. So that's the slope of the tangent. Excuse me. The normal has a negative reciprocal slope. So the negative reciprocal of 1 over 6 is negative 6 over 1. So there's my slope. Same point, right? It just cuts through the point at a right angle instead. So now it's y minus 2 equals negative 6, x subtract 9. Y minus 2 is negative 6x plus 54. X is negative, so let's move these ones to the left. 6x plus y, I got to subtract 54, so that'll give me subtract 56 equals 0. There's my normal. So there's your equation of your normal, there's the equation of your tangent. If you're a visual person, I'll show you what we just did. We took y equals the square root of x minus 1, which is a square root graph. So that's like so, but it's moved down 1. So it's at minus 1, and it looks like that. We went over here to 9, and we found this point, which was 9 comma 2. And then we drew a tangent line. Let's use something we can see here. So there was my tangent line. And we found the slope of that over there to be 1 over 6. My pen going again here. So the slope was 1 over 6. So I used that slope, that point, and I found the equation of that line. And then we did a normal. And a normal simply looked like this. We took this line, which ran through that at a right angle. This was a right angle. And I just used slope of negative 6 and this point and found the equation of that pink line. So that's kind of a visual of what you just did. And that is an application that I'm going to show you of limits. There are others. It's the only one we're going to do with limits. We will do some other applications, but we will rely upon derivatives to do that for us. Okay, so there are a few practice questions in the Onenote pages to follow. Just have a work through those. If you run into any problems, let me know. This is our final section on the limits unit before we get into a review and start preparing for a summative assessment on this material. Best of luck. As always, reach out if you have any questions or concerns, and I'll do what I can to help you out. Thank you for watching.